All right, so we're back. I actually made a couple updates since the last stream. Um, I think the last stream primarily what was done was initializing the structure of chip8. And let me open up the project real quick so we can talk about that. Come on. Okay, I'm guessing I just need to do this. Okay, project directory, let's go. There we go. Let me open up the links until then. So, yeah, I mean, what I worked on last time was a method to start drawing sprites on the screen, right? Basically tying in, well, not exactly, but being able to draw a sprite like, a 0 or a 1, right? A 0 is like I think, consists of, I think, 5 sprite bytes, right? Which represent a 0. I can kind of show you a demo of what I did so far. It's extremely simplistic, probably inefficient, but it kind of works, right? So let's kind of see what I'm talking about right now. If JetBrains ever wants to load, come on. Let me open up tool. Okay, never mind. It's opening up now. Nice. Yeah, this is one negative of an IDE, but yeah, just have to deal with it for now, I guess. Okay, so as you can see, we have main.c, right? And this is what we had last time. What we ended up doing was I did a bunch of constants, right? I think to define the sizes. I realized that that's not allowed. You need to actually, and the reason that it's not allowed is that um, those constant variables are declared at compile time, right? So during compilation. However, if you do these define statements, these are actually um, handled by the preprocessor. So before compilation takes place, this is essentially what takes place. Pre-processing takes place before that, which is where these includes work as well, right? So uh, I just changed these to a bunch of defines. That's pretty straightforward. I also define these draw instructions. Just this is just a function initializer. There's no implementation I've actually put in for these yet. And then this one right here, which is 2D to 1D array index. The reason I did this, we won't need this. We will eventually need this, right? There's a formula which helps you convert like a 2D index into a 1D index. So it's like just a small little function that takes care of that. I think pretty straightforward. The name is a little ugly, but that's fine for now. Then we have draw sprite. So this is what I was kind of worked on before, which is where we try to draw a sprite onto the screen. So I'll show you an example, right? In this example, I've declared the 0 sprite, so like the sprite in order to draw 0, right? And then I pass that out to the draw sprite function, right? I also, part of the draw sprite function, pass a reference to our chip8 struct, right, which we initialized, call it chip8. Then also a window is already a pointer, so I'm just passing the window pointer, the STO window pointer. I'm passing the STO surface pointer. I'm passing start X and start Y. That's essentially the upper left, the top left position for where the sprite starts drawing, right? And then I pass in the 0 sprite, which is what we need to draw, right? In this case, it's these bytes, right? And then the number of sprite bytes. This is something in C, right? Like you don't it seems like you can't, if you're passing in an array, which is essentially just a pointer, right? You cannot determine the size in the function itself, right? Where it's just a pointer. You have to send the size or figure out the size, whatever, right? So you do like either 5, or I'll do like a size of 0 sprite divided by size of 0 sprite of 0, right? Which will give me the size of the array, right? In this case, I just did 5 for testing purposes, right? Just to keep things simple right now. Again, I have a habit of over optimizing, right? Or optimizing before we even get something working. I'm trying to work on that, trying to improve myself in that regard in terms of, hey, let's focus on getting something to work, and then we can start peeling slowly and keep iterating over improving things, right? Rather than having the one stop shop solution immediately. So yeah, that's at least my thought process right now. But yeah, so we call draw sprite, right? Now let's look at what I've worked on in draw sprite. So we have current x and current y. And you'll see reasons for why I declare those. We have pixel width and pixel height. Now, this is a little bit shady. I mean, so pixel width and pixel height exist because if you recall, the display right now is 64 by 32. That's what chip8 specifies, right? If you draw a 64 by 32 window though, that looks pretty bad. Like it's extremely small and you can't really see what's going on at all. So, right, either like you initialize a 64 by 32 window and make it resizable, right? And you need to actually resize all the components which you're drawing onto the screen, right? That I will work on probably doing some sort of resizing. I'm gonna actually note that down, right? So resizing window is one place of improvement, definitely. Or another thing we could do is, excuse me. Ooh, okay. Another thing we could do is make sure that we initialize the window at a big enough point. So we initialize it at 640 by 480, right? That's our window size, right? And this kind of logic can go into the resizing logic as well. You see why? Now, the size of a pixel, like 1 unit essentially of a pixel, right, needs to be scaled up when you scale um, your window size, right? When you increase it or when you decrease it as well, it needs to become even smaller, right? Like how much of the screen actually occupies. The way we do that is we check by, we're essentially seeing by what scale factor have we increased the screen, right? Like the dimensions, right? The width and the height, and we scale the pixel or what we draw on the screen by that same factor. It's pretty straightforward, right? So that's something I did, right? I just thought, okay, hey, we could just do that. We could just scale it by that effect. Then we have current x and current y, right? These are like we're initializing it before our loop starts. Now, if you notice, I have a couple to-dos over here. I haven't actually integrated the display array from the chip8 struct over here. I'm considering whether we even need it. We might need it to get a like easy to represent way to, or sorry, excuse me, we might need it to easily represent what the current state of the screen is or the viewport is in terms of the pixel values, right? I know you can do this via SDL, right? You can actually, there's a, let me show you. If we go into SDL surface, I believe, yeah, there we are. So this is type def struct SDL surface, and we have pixels over here, right? So pixels is a void pointer. I've seen some people work with the pixels array before. I tried messing with it a little bit. I could not get it to work. We can maybe revisit it at some point, right? But yeah. Excuse me. Oof, yawns. All right, so we're looping through from the first sprite byte to the last, right? Going through each and every single sprite byte. For each sprite byte, we need every single bit associated with that byte, because the bit actually gives us information on the pixel color value, right? So we get the actual sprite byte which we want. We check, another thing we want to do is check whether the current Y position is greater than or equal to screen height. If it is, we're going to take the remainder, right? The reason we do this is we don't want to clip. I've seen like contradicting information in different places. Some places say we want to clip in certain situations and not clip in some. What I'm thinking right now is I'm avoiding the clip. What I'll do is, in case we're at a place where Y is greater than or equal to screen height, we'll get the remainder, which what that does is we'll essentially flip back to the top. So you can imagine if we're drawing all the way down and we go past screen bounds, it's going to go back to like the first Y all the way up top, right? So we're doing the same thing for X and Y, right? So if we go all the way down, we're going to like reverse back to the top, right? If we're going all the way right, we're going to reverse back to the left, and same for the left as well. Actually, that's a good point. That's a situation I may need to check. That may be where clipping may take place. I need to think about that. We should, so if going, or not going, but rather drawing all left or top, right? Top, not bottom, right? Should we clip? Should we actually clip draw? None of the pens want to seem to work. Okay, pencil it is. Yeah, so that may be where I think that point may be coming from. I mean, what we could do is we don't need to clip in that scenario either. We could just go the reverse the other direction, right? But the remainder may not work. Like, actually, no, it may work actually. -1 percentage 640. 630, it does work, yes, never mind. So modulo, yeah, I'm an idiot. Modulo with negative numbers will work. So yeah, maybe I should discard this point right now. Yeah, let me just discard this. All right. So yeah, I put a to do here. I was seeing that clipping occurs, but why would we ever clip if we could just do modulo? It doesn't make sense to me, right? This is again a draft function. The real draw function does exclusive OR as well, between the current pixel value and the pixel value you want to set, right, uh, on that spot, right? So choosing 8, since, and actually there is where we would need the display array, because we need to know what the current value is, right? Once we know the current value, we can exclusive OR it with the new value, right? So, and I need to look into why we're exclusive ORing either. I mean, it kind of makes sense. If it's the same color, why would you set it again, right? If it's two different, they're opposite colors, then you would want to change it, right? If it's a change there, then you're going to change it. If it's the same that you want to set as what it is, then don't change it, right? So, anyways, choosing 8 since every sprite will be a byte, i.e. 8 bits Y, yeah, 8 bits YADS. Okay, so what I'm going through is going through every single bit. Here I'm obtaining the individual bit I need, and notice we're going from the most significant bit to the least, right? So we're starting off with the most significant bit, right? And that's how the sprite drawing actually is. So it goes from most significant to least significant, and that takes you from left to right in terms of the X value, right, of the screen. So the higher the x value, you're moving towards the least significant bit more and more. Right? So okay, here need to be using viewport height and width. Yeah, I mean that's already something I've already to-doed. Let me just put the same message here actually. Perhaps scale pixel s. Yeah, I've already done this, so I don't need this message anymore. So SD or rect, right? So how I'm drawing it onto the screen is I'm drawing like a filled rectangle, right? Where the x and y are the current x, current y, which we're keeping track of here, and then we have the pixel width and pixel height, right? Which is the width and height of the rectangle we're drawing, right? So after that we have the if nth bit val equals 0. What are we doing over here, right? So in the case nth bit val, right? In the case that we're drawing white, I'm just specifying that a white color, right? If the bit value is 0, that means white. If bit value is black, it means if bit value is 1, excuse me, it means black, right? So that's what I'm doing here, and then finally updating the surface. Actually, I think this might be the opposite. Excuse me, yeah. What am I doing? So if bit value is 0 is black, 1 is white, right? Okay. Updating the surface. So after each pixel update, I'm updating the screen, right? That's one approach. Another approach would be that instead of calling this here, we could let me put in a to do here. Perhaps call it after every sprite, after drawing an entire sprite. Alright, so instead of calling it after every pixel update, right, pixel here, right, not really, but after drawing every single rectangle, we could just draw it at once, right? But again, we will look into that. Current x plus equals pixel width, right? That makes sense. So this was another thing. So we want to move x times over based on the width of the pixel, right? Otherwise, what's going to happen if we just increment by 1, it's not going to be good because um, we would increment based on that scale factor, right? If we don't do that, what would happen is that you could imagine that if we draw like a rectangle which is 3 units wide, right? And then we move from x equal, and that was like starting at x equal to 0. So basically from x equal to 0 at x equal to 2, let me open this up in Paint. So this is easier to understand. But essentially you can imagine like we have, right, like imagine these as like pixel, each of these like boxes are like a pixel, right? So if we have this at x equal to 0, right, let's just imagine for simplicity's sake, this is x equal to 1, x equal to 2, right? And if we draw something which is 3 units wide, right, and we're drawing, again, the width depends on the pixel width, which is the scale factor, right, which is screen width by viewport width. So for 64 by 32 screen, the pixel width would be 1, where we only want to draw one of these, right? However, right, in our case, the pixel width's around like 10. Let's assume in this case the pixel width's around 3, right? So that means it'll draw all of these with the color that you want, right? With that one color. The problem now is we don't want to increment to x equal to 1 and draw the next color, right? Because this whole block corresponds to that one color. Rather, we want to start that off at x equal to 4. So that's why we increment by pixel width, right? And then we do nth bit minus equal to 1, which makes sense. And we do the same, and we start off at the same x again, right? And then we increment the current y to based on the pixel height, because for the same reasons as this, right? Okay, so let's see how this works. let's just run this, right? So let's see, you will see 0 on the screen, right? And maybe an more interesting way to do this is run this in debug, right? So you can see like each you can see each pixel like being drawn, pixel again, but yeah, you get what I mean, right? We have that. Let me do this. Let's do this. This bugs out actually. See, the resizing event bugs it out. Let me start this again. Sorry. Stop this and then rerun in debug. Right, and then let's do that. So you can see it drawing each and every pixel value, right? Now, calling this render over and over again, update window surface, I don't know if it's less performant than just calling it once at the end, but that's something we can measure. So you can actually see the 0 forming there, which is pretty cool. Again, this is extremely primitive, right? Like, this is like a draft function, as I mentioned. There's a lot to improve here, but I mean, it's not bad for starters, right? So yeah, that's the draw sprite function. I'm going to leave that now. If you recall, my first objective was um, making sure that we initialize the structure. Second was tying the display in with the sprite drawing, and then the third was the display from the structure, just to be clear. And then the third was starting to work on the instructions. So what we can do here is, I'm thinking rather what right now, should I start working on the instructions or continue with the draw sprite stuff? I think what I'm going to do is start working on some of the instructions, and maybe we can also get to the draw sprite stuff, because the instructions themselves are not complicated at all. It's like very simple, just logical operations, right? So let's actually look at the instructions. So let's go, right? So clear the display. This is the first instruction. There's also a 0 and n, right? Which is corresponds to system address, and it's ignored by most people. So we can ignore it as well for now. So let's do that. So first one is 0 and n, right? And it should take in a struct chip8, okay, chip8 pointer, right? What's the issue? It can't start with 0, of course, so we just do like operation 0 and n, and that's how we're gonna follow the structure for. We're gonna do the same for dxyn as well. All right, next one is clear screen. So 0 and n, we don't even have to implement. Clear screen is 00 E0. E0. Let me actually maybe put a comment in with the sys instruction. All right, and then next one would be CLS instruction. All right, and clears the display. Ignore. Right. So let's actually implement this, right? So this takes in our chip8, right? Okay. So what we need to do is clears the display. What does this mean, right? This essentially means that we probably want to set all the pixel values in our display array to 0. And that should be very straightforward, right? What we do is we do a for loop, right? Size t index equal to 0. Let's just do pixel index to be clear. Pixel index less than, okay, yeah, so I mean, actually here we have the sizes available, right? So in this case, pixel would be viewport width times height. And viewport may not be even the right word, but again, let's ignore that for now, right? And then we have pixel index plus equal to 1, right? We increment over each and every single pixel, right? So now what we would do is we want to set all of this to 0, right? And here we're only setting, so you can imagine, right? This is how I at least maybe want it to work, right? Our display array is our record of what the display uh, is holding, right? Or rather what it should be changed to, whatever. It's like a buffer essentially of what the display is going to actually display, right? And then there's the actual display, which is not really actually tied with this at all, right? STO has its own like pixels, I showed you pixels array, right? Which is a void pointer. Ideally, we want this record to update this, right? In a in like a regular fashion, right? We don't want these to be out of sync, right? We want these to hold the same information, right? If this has something new which comes in, updates are going to go here first and then update this, right? So just something I want you to keep in mind, right? So let's do that. And perhaps we should maybe have a we will need a function, right? Something like draw or update display, okay, which is going to take in strict chip8 pointer, right? Oh my god, right? And it may also, it will probably take in STO window, STO surface, right? And what this will be responsible for is update the STO display as per what's happening or what's held in the chip8 display array. Okay, so yeah, and that function we're not going to call inside this operation. This operation is just responsible for updating that display array, right? The syncing of the two displays, that's in that separate function which is called update display, right? So let's do that. So we go through each and every single, we're going to need to access that display array. So let's use chip8 of display of pixel index equals 0, right? And that should be sufficient, right? So yeah, that's essentially the clear screen instruction, right? Uh, we can move on to ret, which is return from a subroutine, right? So that would be 00 EE, right? And this is ret instruction return from subroutine. All right, so let's copy this, let's implement this as well. All right, weird that copy didn't take place properly, whatever. All right, and let's see. The interpreter sets the program counter to the address at the top of the stack, then subtracts 1 from the stack pointer. All right, let's think about what's going on. So again, we have our call stack, right? Let's open this up again, right? And is there an easy way to like get rid of all this? Like, come on, there needs to be a better way. Let me open whiteboard for now. Just get that a little bit better. Microsoft whiteboard. All right. Actually, let me open that one again. That's like an infinite board, which I like. All right. Let me get out of here. All right. So we have our stack, right? Right, which we usually imagine vertically, right? Need not be vertical, right? It's just an array, right? You can imagine it horizontally as well, or it just gives a good understanding since we're referencing top and bottom, right? So let's do that. So let's just do red. All right, so this is the top, right? Which is some index, right? It at max it's index 15, right? In an array, because that's the maximum we can go. Let's assume this is equal to 2, right? Actually, let's just assume this get 1, 2, 3, 4, right? It's equal to 4, right? So we're 4 levels deep in terms of our calls right now, right? That's what the stack is telling us. And this top is held by the stack pointer, right? And this whole thing itself is just the stack, right? So stack of stack pointer gives us the top, right? When I say stack of stack pointer, I mean stack index stack pointer, right? Stack pointer is just an index, right? Not an index actually, excuse me. Sort of is an index, but it's the memory address of this location, of this index, all right? So subtracts 1 from the stack pointer, right? So the interpreter sets the program counter to the top of the stack. So when we're returning back from a subroutine, this top portion, what does that mean? It's talking about the previous function that we were in, the address of the last executing instruction there, right? So let's actually do maybe an example. Let's do like this is function A and this is function B, right? So let's say function B, A calls function B somewhere over here, and this is, let's say, like at address 31, right? Just an example, right? And then at address 32, we're doing some printing in function A, and 33, we are doing XYZ, doesn't matter. When we make this call to B, right, before it transfers control to B, it needs to remember where it was before so that when B finishes executing, it can return back to A, right, and execute line 32. What does it do? It stores line 32 in the actual, at the top most level of the stack, right? So it stores 32 there. And then it transfers control to B, right? And B maybe like 1000, right? Let's just assume, right? So it's executing, it changes the program counter to 1000 after that. So program counter is like whatever is the currently executing instruction, give me the memory address of that. So let's say, I mean, logs something, right? So now it's executing this, it executes, and then when we press return, what happens is return changes program counter value to whatever's on the top, right? Which is what the instruction we're literally implementing, ret, right? And we need to change, essentially get rid of this, right? We don't want this anymore. The stack pointer should now reference the previous, the actual previous, the previous function, right? So in this case, let's say there was like another function before A, right? Which A got called from, which is like the main function, right? Wherever A got called, that maybe that memory address may be stored here, right? And that's what we need to reference instead. And then when we do, so that when we do the return here, it returns back to main, right? Makes sense. So yeah, not a great drawing, but I hope that was understandable. If it's not, just let me know. We can go through it again. It's not a problem. So again, what we need to do is set the program counter to the top, to the address at the top of the stack. So just do like chip8 of PC would equal what? We'd want to make it equal to the excuse me, you'd want to make it equal to the top. So you want to make it equal to chip8 of stack of chip8 of stack pointer, right? Makes sense. And then we'd want to subtract, so we'd want to change the value of this stack pointer to minus equal to 1, right? And actually, I don't like this here. Let's do that. Okay, cool. That looks good. All right, so we change the program counter value and then we decrement the stack pointer, right? That makes sense. Let's move on now. That's literally that's how return works, right? It works based on a bunch of like existing knowledge, which is like a bunch of these registers which have different information. It's just modifying simple stuff though, right? So next one is jump, right? Which is what happens when we're doing transfer of control. Like we're jumping from one block of code to another, right? Like kind of like what a go-to statement does, in fact. So let's do that. Let's do what are we? 0 or 1 and n. Okay. Actually, I don't even know if I should call these this. We could just call it sys, or let's just do op sys. Let's just do op CLS, right? So it's understandable. And then what we can do is we can define like a map, which maps between different between like maybe like a parallel array, because I don't know if maps exist in C. I've not used a map before in C, but like a parallel array of corresponding the instruction, the opcode to the actual instruction, right? So whatever. Okay, so 0E is ret, and then this one will be JP, right? Which is just JP instruction jump to location and all right, whatever. We need to also make those modifications here. CLS ret, then we have jump, right? And we kind of want the same argument, right? All right, interpreter sets the program counter to n. All right. So where is this n coming from? This is coming from the actual op code, right? So op code is going to be 1 n, right? So in this case, what happens is we need to extract that n, right? How do we extract that? We would extract that using like a bit shifting, right? Kind of like what we did over here, where we try to extract every single um, excuse me, we try to extract every single uh, bit, right? It's just a single bit, right? So what we need to do is trying to think. Okay, this is actually important. I should have read this out. These distinct the following variables are used. N or ADD are a 12-bit value, the lowest 12 bits of the instruction. N is a 4-bit value. So each of these are 4-bit values. 4-bit, 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 right? X a 4-bit value, the lower 4 bits of the high byte of the instruction, Y a 4-bit value, the upper 4 bits of the low byte of the instruction. I need to look at what high byte and low byte are, but that's fine. KK or byte, an 8-bit value, the lowest 8 bits of the instruction. All right, so we need to extract the lowest 12 bits of the instruction, right? And. So how do we do that? So let's look at bit shifting. Right, let's just bitwise operation, sure. So we need to extract like, let's just imagine like a simple example, simpler example rather than 16-bit, let's go 8-bit, right? So let's do, if I can draw the shape real quick. Actually, let me not draw the shape, just do it free form. Let's do 1, 1, 0, 0. How do we actually extract 0, 0 in this case, right? So let's just say this is num, right, which is equal to 1, 1, 0, 0, right? So let's think about how we would actually extract 1, or sorry, 0, 0 in this case, which is the rightmost 2 bits, right? So let's think. So you can bit shift, right? So what is bit shifting? We're actually shifting the bits in a particular direction. We can either shift them left or we can shift them right, right? And we can shift them by certain amounts, right? You can shift them by 2, you can shift them by any n number, right? You can shift them by 1, right? So what does it mean to shift something by 1? If we shift left, right? So I believe it's like this, right? If we shift num by 1 to the left, what would happen, right? So this would essentially go here, this would go here, this would go here, right? Let's look at what that looks like. In that case, our number would be a 0. So this would go here, right? So we'd have 1. Sorry, this would be 1. This would be 0, 0. We'd have 1, 0, 0, 1, right? So essentially, you can imagine it as starting, like getting rid of this and just putting it here, right? We're shifting this side to this side, right? So what would a right shift look like, right? In a right shift, we're essentially starting it from so this would go all the way here, right? This is a left shift, and then there's a right shift, which would be 0. This would go all the way here, and then 1, 1, 0, right? So we have 1, 1, 0. So you can imagine that as just getting rid of this, right? That's kind of how it is. Not necessarily, right? Because if this is 1, it's not getting rid of it, right? But it's moving this to this position by 1, right? So what happens if we do it by 2? In that case, both of these would move to, so we have something like 0, 0, 1, 1, I believe. So it's as if we're moving this by 1. So let's see, 0, 0, 1, 1. Yeah, that makes sense. That's for the right shift, right? So what do we need? We need 0, 0, right? How do we just get 0, 0, right? So first we need to basically chop off this part, 1, 1. We need to get rid of 1, 1 somehow. Let's see, let's think of how that's possible. Let's look at bitwise operators. In expressions below, an indication of a bit position is counted from the right. Okay, yes. For example, binary is usually bits that are 0 become 1 and those that are 1 become 0. Okay, that's fine. Resulting at that's 2's complement. That's okay. And operation. Equal length binary representation performs logical error. Right. Okay. The operation may result. Okay. Yeah, I think what we need to do in this case is we need to AND it with sorry, 0, 1, 1, 1, right? That would be the main part of it, in fact, not the shifting operation. Excuse me. I think I was getting confused. Shifting operation comes in later, so we'll see. Right. So imagine 1, 1, 0, 0. How do we just get 0, 0? We need to AND it with another number. How do we get rid of a number using AND, right? How do we produce a 0? If you do AND with 0, right, regardless of what you AND 0 with, the outcome is going to be 0. So we put zeros here, right? And then if we want a number, the way we would do it is we AND it with 1, right? If the number was 0, we're going to get the number, which is 0. If the number was 1, we're going to get 1, which is the number, right? So 0, 0, 1, 1, right? Now in this case, right, these are all in hexadecimal, right? What we would need is 0 FFF, right? Which is essentially this number. So FF is just 1, 1, 1. F is just 1, 1, 1, 1, right? That's F, right? So imagine 0 FFF is just 0, 0, 0, 0. That's corresponding to this, and then for the rest it would just be 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, right? For all these Fs, right? So we're getting this 12 lowest 12 bits, right? So let's actually do that, right? So we need the lowest 12 bits from the opcode, right? So, and what we're gonna end up getting is a 12-bit, so, but we need to store it in a 16-bit because, I mean, there's no data type for storing 12 particular bits, so let's do U16N of n equals, we need chip8 opcode and 0x, which is to signify hexadecimal, 0FFF, right? Now that we've got that, we need to jump to that actual instruction. So we need to set chip8 of PC will equal n. It's pretty much that simple, right? Also, right, interpreter sets the program counter to n. Okay. This should work, I imagine. So yeah, lowest 12 bits, that makes sense. Yeah, it should work. Yeah, that makes sense. All right. So this is pretty much it for the jump instruction. Let me include the description since we're following that. Let's just do that to make it more clear. Right, and then we have 2 n, right? So let's do that, which is what? Call address. Okay, call subroutine, call instruction, call subroutine at n. Okay, cool. So that's the next function. Let's implement that. That should work in a similar fashion. Again, we probably need to do this extraction, right? So let's do this. Oh, why that keeps happening? Oh God, come on, please. All right, thank you. Okay, so call subroutine at n. The interpreter increments the stack pointer, then puts the current PC on the top of the stack. Makes sense. This is when we're calling a function. Again, goes back to this example that I was talking about, where we have function A, function B, right? When we're calling B, we need to do a set of operations before we actually transfer control to B, right? So again, we're just copy paste this part, right? Which is just calling n, right? I think this is, by the way, called like a bit mask, this little thing. It's because we're like masking to obtain a certain, like certain bits, right? But anyways, so the interpreter increments the stack pointer, then increments the stack pointer. So we need to do that. Chip8 of stack pointer plus equal to 1, right? Puts the current PC on the top of the stack, right? So chip8 of stack, excuse me. Actually, we can of course, as you can see, you can probably just shorten that representation into the following, which is chip8 of plus plus chip8 stack pointer, right, would equal uh, the current program counter, which is chip8 of PC, right? Makes sense? And then we want to subtract, sorry, not subtract, where am I? Then we want to set the PC to the current value that we obtained from the opcode, which is NNN. Right? Makes sense, right? We don't need this. So cool, that was the call instruction. Again, this is like very simple stuff, not too complicated, right? Then we have skip next instruction. Okay, cool. Yeah, we're getting into maybe a little bit more involved stuff, right? Like where we need to do maybe a little bit more sophisticated bit masks, right? So let's do that. Sure. So skip, right? Skip instruction skips next instruction. If Vx not equal to Vk, not equal to Kk, excuse me. Yep. All right, and we'll see what Vx and Kk are. Vx again is that general purpose register, right? And X we're getting from the actual opcode, right? So, actually, let's copy that. Copy this. All right. Then let's see. All right, so the form is 3xkk. All right, let's get kk first. All right, so u int 8t kk this would be pretty simple. This would just be chip8 of op code and 0x00ff. Right, that's where kk, the value of kk is. Is there an issue here? Oh, and sorry, excuse me. We want to do something similar for x, but now you see where bit shifting is important, right? For x, what we need is this portion right here, but we want to bit shift that by 8 so we get the actual value of x, right? Not like instead of getting like if x is 1 1 1 1 1, right, or 1 in x, like yeah, if x is 1 1 1 1 1, right, which is 16, right, f, right, in that case we don't want to get f 0 0, we want to get 0 0 f. How do we do that? We would want to bit shift this to the right by 8. Let me just make sure, right shift bit and C. Yeah, I've visited this page before. So, okay, left shift is, yeah, it's the direction of the arrow. Okay, cool. So, once we obtain that, we want to make sure that, okay, skip next instruction if Vx equal to Kk. Vx, right, now if chip8 of V of X, right, is equal to chip8 of Kk, right, if Vx equal to Kk, right, in that case, what would we want to do, right? oh, excuse me, not chip8, okay, it's just KK, right? In that case, the interpreter compares the register VX to KK. If they are equal, increments the program counter by 2. You see why incrementing the program counter by 2 is important, right? If they're equal, excuse me, uh, program counter plus equal to 2, right? Cool. Increments the program counter by 2 if they are equal, right? Uh, and that's this skip if equal, skip equal, right? Let's do skip. It's called the skip equal actually. And this is wrong. Equals KK. Yeah, that's the 3x KK. And then we have skip. And actually, instead of calling it skip EQ, we actually get rid of these descriptions. Not necessary. Just to make life easier, you know. All right. Cool. So, and then we do not equal, right? Skip not equal instruction, skips next instruction if it's not equal to KK. So it's exact same thing as this. It's just literally the if condition is going to be different. Not equal, right? If Vx is not equal to KK, then we increment the program counter by 2. Simple, right? Next up, what do we have? So that was 4xkk. Then we have SE, right? Similar to this, but let's see what Vx and skips next instruction if Vx equals Vy. Right, so let's do that. Skip equal. It's a little bit different though. Perhaps we can like lump these together. Skip equal. What's the difference here? KK. Skip equal Vy. Right. If Vx equals Vy. Let's do that. Skip equal KK. Alright. And instead of this, we do skip equal Vy. And instead of obtaining KK, so let's look at the actual opcode. Vx and y and 0. Right? X is the same, right? Y would be 0x 0 F0, and we want to bit shift by 4 to the right actually, right? So yeah, that would give us Y, and then we'd want to check whether chip 8 of Vx, that's not what I want, would equal chip 8 of Vy, right? And in that case, we want to increment. Cool. That's not what I want. All right. Next, go after that to, let's see. Next up would be skips. Okay, LD, right? Load, I'm assuming. Yeah, it is load. And this should be equal actually. Skips next instruction if Vx equals 1. Yeah. This is LD instruction. Puts KK loads KK into Vx. Right. Cool. So that should be pretty straightforward as well, actually. So op LD, right? We still need X, right? And X is in the same position, right? and we still want kk, right? So it would be something like this. So yes, we obtain kk, we obtain x, right, which we have already done in the past, and we set chip8 of vx equal to kk. Simple, right? That's pretty much it. Interpreter puts the value of kk into register vx, right? Cool. That's that. Then we move on to op. Let's see, add. Right. Add instruction, right? Uh, what do we want to do here? Add kk to vx. So essentially, vx equals vx plus kk, I believe. Yep. All right, cool. So let's do that. Let's do op add, right? Vx kk again. We need to still include those, and then we just should do plus equals. Right? That's pretty much it. Vx equal to Vx plus kk. Yep. Next up, we have another load, right? Set Vx equal to Vy. So let's do this. Load kk, load Vy. Let me actually re-reference this kk. Loads Vy into kk, I believe, right? Yeah, cool. So we just copy this. Yeah, okay. We want x, we already have that, and we want y, which you can just get from here, right? And then we'd want to store chip8 of vy. Cool. All right. And this wouldn't be kk, this would be vy. All right. So cool. That makes sense. So next we can move on to the next. So as you can see, this is a little bit like simple stuff we're just implementing, right? Nothing too complicated. It's just like small little operations that we kind of are repeating certain tasks. But yeah, right. So then we have or, right? The pretty simple operation, or just do that. Or, right? Let's do or instruction vx equal to vx or vy, or vy, right? Okay, cool. Let's do, we need x and y, right? Same way we always obtain it. And then what we want to do is, I believe this should work. Uh, yeah, so essentially or operation is just that, like the little straight line, right? So we want to do that. I think that's good. Then we have and, right? So this is the basic uh, logic gates, right? Logical operations, right? In this case, we want and, right? And I believe, yeah, Vx and Vy, right? copy that, and instead of this we just do and. Let's either leave it. Alright, then we want another and, or sorry, excuse me, exclusive or, right? Exclusive or, let's do that. This is, we were talking a little bit about this before. Let's do that. And I'm assuming it's the same exact thing. There's actually exclusive or built into C, I believe. I forgot what the actual operator is. We'll have to check that out. XOR. Right. Let's see. XOR operator. Let's see. Oh, okay. So like this. Right. Cool. Yeah, this is OR. This is XOR. Left shift, right shift, not, and. All right. Cool. Okay. So let's go back. We have another add. This is VXVY. Right. So let's do something like this. Right. We need to do a find and replace. VX and VY. Right. Without carry. Right, okay, cool. I guess we'll just do it like that. No, that's not what I wanted. Oh god. I didn't want and, I wanted add. Okay, here we go. Okay. Okay, so I'm just gonna base it based on op, add without carry and add with carry, right? So let's go back. Vx equal to Vy and Vf equal to carry. Carry bit, right? Okay. Let's go back, and I need to recall actually. Okay, what? This is different. Never mind. This Vx equal to Kk. Vx Vy. Yeah, okay. This is different. This is different. Let's obtain this here. Vx chip8 Vy, right? And how do we obtain carry bit? I believe it is some sort of AND operation, I believe, right? Is it AND? Let's see. I recall doing this sometime back. Let's see. Cool. Let's go 1 1 1 1 plus 0 0 0 1. How do we know it's going to be carry bit or not? So I mean the 1 plus 1 is of course 1, right? But that takes a carry here. 1 plus, actually let's just do 1 1 1 1 1. Let's just do that. That will be 1 plus 1, which is 1 0, right? Let's see. Hmm. I mean, hmm, we need to do like a single bit, like add every single bit to each other. Is it like that? And then figure it out? Should there's an easier way, I think. It's an exclusive or hmm, the result is greater than 8 bits, VF is set to 1, greater than 255. Okay. Otherwise 0. Only the lowest 8 bits of the result are kept and stored in VX. Okay. Okay, I mean, what we can do is something like this. We can do if, let's just do like uint 16t sum equals chip8 vx plus vy, right? If sum is greater than 255, I believe this is 0xff. And why am I doing that? Sum greater than 0xff. Then what we'd want to do is set the carry flag to true. Chip8 v0xf, right, equal to 1, right? Yes. Uh, what's oh, that's okay. Cool. If that's the case, right? If not, then we don't care, right? We've actually, yeah, we do care. Else it should be 0 for that operation, right? We don't want it to carry. We want to override the value based on the actual. So, and then at the end, we want the lowest 8 bits of sum, anyways, to store in Vx. Chip8 of V of x will equal sum and 0x 00ff, right? And okay, yeah, okay, that works. I mean, I'm sure there's a better way, probably, but that works for now, right? That should work. So let's go ahead then. Subtract, right? So equals not borrow. Okay, I figure out what that is. Subtract sub instruction where Vx will equal Vx minus Vy, excuse me. Set Vf equal to not borrow. If Vx greater than Vy, then Vf is set to 1, otherwise 0. Vy is subtracted from Vx. Then Vi is entered. Okay, cool. So let's do that. Op sub, we need x and y, yes. if chip8 of Vx is greater than chip8 of Vy, in that case, what do we need to do? If it is greater, then we need to set Vf to 1, right? So chip8 of V of 0x, V of 0xf would equal 1, else we'd want to set this to 0, right? And it depends also now. So if it's greater, then we want to store Vx minus Vy as the result. If not, we want to store Vy minus Vx, right? Makes sense because we're dealing with unsigned numbers. We don't want a negative answer, right? Chip8 of Vx minus equals chip8 chip8 of V Vy, right? That makes sense. Okay, I don't know why it minimized everything. I wanted to expand. Okay, here. Okay, and if not, we'd want chip8 of Vx to equal chip8 of Vy minus chip8 of Vx. Makes sense, right? Right. Okay, cool. And that is essentially the subtract function, right? Okay, next up we have SHR. If the least significant bit of Vx is 1, then Vf is set to 1. Okay, it should be pretty simple as well. Void op SHR. Just copy this actually. SHR instruction. Okay, SHR. If the least significant bit of Vx is 1, LSB of V of x, rather Vx equal to 1, then rather equal to 1. If so, Vf equal to 1, else Vf equal to 0. Vx is divided by 2. Vxy equals 2, right? And division by 2 is kind of like a right shift. It is a right shift, in fact. So, like, I think I showed you before, but like 1 1 1 1, for instance, right? In this case, what would happen is we'd probably end up with 0 1 1 1, right? As when we shift to the right. And actually, I was wrong about right shifting. This, so when we right shift this, it doesn't go here. Rather, it just leaves the picture, right? So this turns into a 0. So 0 1 1 1 1. So yeah, I was messing up my right shifting when I was talking about it, and excuse me for that. But yes, 0 1 1 1 makes sense. Yeah, that makes sense. Let's make sure I'm talking about the right thing. Let's see, bit shifting example. So 0 0 1 0 to the left would be 0 1 So left would be yeah, 0 1 0 0. Yes. Let's look at the right. Yeah, so that would be 1 0 or 0 1 0 1. Yeah, 0 1 0. Okay, yes, that's correct. This doesn't go here. If they did, it would be 1 1 0 1, which is not true. It's wrong. Okay, so 0 1 1 1. All right. In that case, what's happening is like uh, it's essentially like dividing by 2. 1 1 1 1 is like what, 16. 16 by 2 is 8, which is 1 1 1, right? So let's do that. Void options. I want to type define this actually. Uh, Not that it matters right now, but just for convenience. Okay, let's go back. 8xy. Okay, so let's obtain x and y. Right? What's wrong here? Opposite chart. Opposite chart. Yes. Oh, that's right. Oh, not that. Sorry. It's here. That's the problem. Yeah. Okay. Cool. We have x and y, and then if least significant bit of vx is 1, then okay. If chip 8, and that's actually easy to figure out as well. So that would be of v of x and 0x0001 is equal to 0x0001. Okay, yes. Then we want to set this, not vx, but rather 0xf to 1, else we want to set this to 0. Right, and let's see, yeah, if we, otherwise 0, then vx is divided by 2, right? So we want it simply to chip 8. Let's just copy this actually, vx. Can you do this? Right shift equal to 1. We want to right shift by 1, not by 2, right? So that's like right shift by 1 is like division by 2. Right shift by 2 is like division by 4. Okay, I didn't expect this to work, but this works, I guess. Cool. All right. What else do we have? We have a good amount more left, actually. Let's try to get past these. So we have sub n. So what does this mean? Vx equal to vy minus vx. Set vf to not. So if vy greater than vx, then vf is set to z1, otherwise 0. Then vx is subtracted from vy, and the result. Okay, I think I was wrong here. Subtraction. Okay, so never mind. Vi is subtracted from vx. So this is actually what happens in this instruction. This is not the case. Yeah. Okay, and we want to probably replace this. Sorry. Ob sub with ob sub. But actually, we don't need to replace that right now. Let's call it ob sub n. Sub n instruction. Vx equal to vy minus vx. Okay. Sub n, get xy if vx is greater than vy, and vf is set to 1. The same, right? Oh no, excuse me. Vy is greater than vx. So it's kind of opposite here. If vx is greater than vy, this is 0, this will be 1. Right? Y is greater than, otherwise 0. Then vx is subtracted from vy, result is stored in vx. Okay. So essentially we're doing vy minus chip8 vx. Yep, that's op sub n. Then we have SHL. Set Vx equal to Vx SHL1. If the most significant bit of Vx is 1, the Vf is set to 0, 1, otherwise to 0. Then Vx is multiplied by 2. Cool. So this is like left shift. Right? Instead of right shift, we're left shifting. So let me copy this. And we will, it's called SHL times equal SHL instruction. Cool. Change this to SHL. We have X, Y, I believe that's all we need. The most significant bit this time. So if the most significant bit, that's like this basically, is 1. The most significant bit yeah, okay. If the most significant bit is 1, then Vf is set to 1, otherwise to 0, then Vx, instead of right shifting, let me left shift. Multiplied by 2. Okay, cool. That works. That makes sense. Then we have SNE, skip next instruction. Okay, this is similar to that. If Vx not equal to Vy. Let's go back here. Where do we have skip? Yeah, skip. We do not equal. Okay. Yes, skip not equal instruction. Actually, KK Vy. Actually, I mean. Okay, cool. We have a new skip not equal Vy. Vx not equal to Vy, right? Yes, okay, cool. So let's go back here. We need y and x. Let's do that, right? If Vx not equal to Vy. Okay, so Vx not equal to chip8 of of Vy. In that case, we want to skip. They are not equal. We increment program counter by 2. Cool. A and N. Okay, what is this? Set index register. Okay, I don't think we even defined our index register. Actually, let's do that. Right? I don't think we did. Yeah, we didn't actually. So it's actually mentioned here. Index I. Okay, that's the horrible way to find it. Nothing's here. Stack pointer, pseudo registers, program counter, you store stack pointer, it is stack interpreter, nested subroutines, display, Okay. Sound produced has only one tone. The frequency is decided by the author of the interpreter. Time decrements. Okay. This is another interesting angle, the audio. So we have to look at that. It's interesting that there's math, graphics, everything all in either these instructions encoded. Okay, let's get back to this. Sorry, mind went elsewhere. Okay, value of index register is set to n. Inherently, I mean, index register is going to be, let's call it index. Okay, so load. It's again a load. So let's go load index. Loads okay, n into I. Right? Yes. Cool. So let's search load. Let's go here. Let's copy that. Index. I believe that's it. Yes. Cool. So for this, what we want to do is see. We need to obtain n. I mean, there's a simple way for that. It's right here. Instead of x and y, we obtain this, and then we load it into our index register. So, right. Cool. That's it. I mean, that's all that instruction is. Then we have bnnn, which is jump, essentially another jump instruction. So let's go to a jump. We need to replace this with jump nnn. Sorry, excuse me. nnn, place all. Boom. Other one's gonna be v0. 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 So we obtain the value of nnn, right, and we set the program counter to nnn plus chip8 of I'm looking for v of 0, right? That's it. Okay, then we have cxkk rnd, random byte and kk. Interpreter generates a random number which is ANDed with the value of kk. Result is stored in dx. See instruction 8 for more information on AND. Okay, that's fine. So let's do, this is an interesting one. So void op rnd. Let's just do that. Ran 0 to 55 and let me store this in dx. Ran and kk. This is called ran. operand. We still have x, right? And x is in that same position, and then we need kk. We don't need bit shifting for this. ff, right? And now what we need is uh, generate random numbers. Let's see, 2 raised to 8. Yeah, 256 makes sense. We need a uint 8. How to generate a random int in C? Bounded. We need it bounded. Standard library. Okay, cool. Standard library. Thank you. Let's just use that. It seems pretty simple. Include standard lib.h. Cool. What we're going to do is uint 8t equal random equals rand percentage 0x rather and percentage 256. We need 256 because like 256% is 256 is just going to be 0, right? 255% 256 still goes 255, right? So 0 and 1. Now this is not going to return us as limited randomness. Really? Hmm. Hmm. Okay, I mean there'll be some skew, but that's okay for now. Again, this is something we can improve. Let's get something working first for the over optimize. Alright. 0x ff. Okay, cool. Okay, random number. Cool. So we do that and we AND the value with kk and store that chip8 v of x will equal random and kk. That's it. Okay, cool. Then we have the draw, right, which is the one we were working on, which we'll need to continue working on. Draw instruction should just be drw. Draw instruction display in byte sprite. In byte sprite starting at mem location I at px ey set vf equal to collision. We'll come back to this, right? This is going to be probably the most complicated instruction that we have, right? Okay, let's go up next. Skips next instruction if the key skips next instruction. Okay, so this is another skip. Skips next instruction if key with value of ex is pressed. Checks the keyboard, and if the key corresponding to the value of the x is currently pressed, in the down position, PC is increased by 2. Okay, so now skip equal, this would be like a skip equal kb, right, keyboard. Skips next instruction if vx vx is what do we need here? We only need x, right? We need x, that's it. So now what we want to search for is if, how do we check that? I mean, again, this is not a map, so we can't index it using map. So okay, let's assume, okay, we need to implement some sort of mapping, but and introduce that. But let's do this for now. Do we shouldn't assume what? Oh, I'm an idiot. Too much Python. We shouldn't assume that Vx will hold the index to the correct key in our keyboard array. Need to define map. That can be a function as well, right? It doesn't matter, but we need some sort of mapping. So essentially what we will just do for now is we'll just do chip8 of keyboard of chip8 of Vx if this is equal to 1, then we skip, right? And 1 corresponds to down position. If not, it doesn't. I mean, ideally what we need to do is, actually I don't know yet. We need to implement that map. That map will give us the answer to fixing this, right? Next up we have a couple more. Okay, skip. Uh, okay, Vx is not pressed. Okay, so same exact thing. Very similar at least. Skip not equal kb. Skips next instruction if kb char Vx is not pressed. All right. And we will do that. Skip not equal kb. We should assume, okay, if this is 0 then we should skip, right? Next up we have another load, Vx equal to delay timer value. Okay, so we have sound timer and delay timer. Okay, cool. Load delay timer, loads delay timer val into Vx, right? Cool. So let's go there. Right, okay, this is, yeah, we don't really need any, we just need x, yeah, for Vx. V of x equals chip8 of delay timer, right? That's it, yeah. Next up we have wait for key press, store the value of the key in Vx. All execution stops until a key is pressed, then the value of that key is stored in Vx. Okay, then the value of that key. Is it like the ASCII value of that key? Could we assume that? I don't know. Hmm. Or if we, like, uh, we can make up our own encoding of those keys, right? Which is again goes back to that mapping, but wait for a key press. Okay. All right. Load keyboard press. Loads pressed key to Vx. Okay. Load key press, right? So we have the value of x. Then we need to continually iterate through, so maybe something like this, pool key press equals false, right? While not key press, right? What's wrong here? While not key press, what happens? You need to go through every index of the array. So for size t, kv char equal to 0, kv char less than num keys, think it, and then kb char plus equal to 1, right? If there may be a faster way to check this as well, but if okay, we need to put that to do here too. Look at test rounds for example usages. Okay, now if chip 8 of keyboard of kv char is equal to 1, that means it's being pressed, then we need to store that kv char. So chip 8 of kv char, or sorry, excuse me, of vx equal to kv char. So we're storing that index essentially, right? And this just keeps going through all the keys, right? And then we also want to set key press equal to true, and we want to break, right? Makes sense. Else we just keep continuing. Okay, so fx15 set delay timer equal to vx. Okay, load delay timer. Okay, so this is the opposite this time. Load delay timer val loads vx into delay timer. What? Yes. Or rather just here. Load delay timer val. What? Oh, that's what I got. Okay, cool. So we get x. Yep, so we set delay timer equal to this, right? And yeah, I mean that's pretty much it. Set sound time. Okay, so it's kind of the same thing. Sound timer equal to the value of vx. Load sound timer val or vx into sound timer, and we just copy this. So delay timer even sound timer equal to vx. Yep. Okay, cool. Then we have add. So add the values I and vx are added, stored in I. Okay, cool. So we go back to add. So add index vx or other I equal to I plus vx, right? So that It's kind of like without carry. We don't care about the carry thing right now. Carry bit. So op add index. Right, just to make sure. Yeah. Okay. We get the value of x. That's all we care for, and we store plus equals chip 8 v sorry not v index plus equals. Yep, that should be good. Cool. Then we have set I equal to location of sprite for digit vx. Okay, value of I is set to the location for the hexadecimal sprite corresponding to the value of vx. Okay, interesting. See section 2 for more information on the hexadecimal font. Okay, so we need to define like a global variable. It's not even a variable actually. It's to define constant array in C. Const we don't use a define directive. So another thing is map data structure in C. No, not C++. As map. Okay, yeah, so that's the one thing. Okay, what we can rather do is go back here. Let's look at what, okay, value of I and Vx are added. Okay, value of I is set to the location for the hexadecimal sprite corresponding to the value of Vx. Okay, interesting. Right, because that's stored in memory, right? Okay. Stored BCD representation of Vx in memory locations I plus 1, I plus 2. BCD coded decimal. Vx That's easy. Okay, that will be fine. Okay, so set I equal to location of sprite. Value of I is set to the location for a hexadecimal sprite corresponding to the value of the x. So yeah, I mean, data should be stored in the interpreter area of chip8 memory. 0x00 to 0x1ff. Okay. And if we go back to memory, 0x00 to 0x1ff. So first 512 bytes. Okay, cool. So maybe we can, yeah, maybe we can do something like this. Void initialize sprite data. Right, so we just need struct chip8 chip8. Okay, so what we might want to do is have something like this. Okay, and essentially what we would need to do is something like this. So chip8 of memory, sorry, mmap, I think, yeah, mmap of 0 equals, so to sprite bytes for 0 equals 0 except 0 except 0, right? And similarly for 1 would be 0 except 90. Then for 2 would be 0fx90, sure. And then for 3 would be 0xf0, cool. And repeat we need to repeat the process for 1, right? So for 1, oh shit, okay, wait, we have another one here. This is 3, then 4. What? Okay, didn't mean to do that. Okay, we'll fix that. Okay. 3, 3, 3, 3, 3, 3, 3. Okay. What's wrong here? Okay, anyways, actually I'm an idiot. I didn't need to do that. 5, 6, 7, 8, 9. Oh god, botty. I'm a bot right now. Why is this showing this? I don't get it. Okay, maybe it's just, and this is for 1, right? So 20602020. 202070. So yeah, I mean, are these all like 1, 2, 3, 4, 5, 8 by 5, right? Yeah, these are all 8 by 5. So okay, we'll do like this for now. In case we need to actually load more sprite data at some other point, we can maybe think of something else. But I think this is fine for now. And this will be 10, 11, 12, 13, 14. Uh, just do something like this actually. Uint 80, actually uint 16t start and start location equals 0. Uint mem start. Just include this actually. Then we can just do mem start. I'll just maybe put a to do here. Do some checking for mem start value, some assertion for mem start value, and also another thing we need to do is and ensure no spill over to IDX 512 or above of mem. Okay, mem start. Is there a way assign multiple assign array to another array and see? Let's see. Maybe we could do something like that. Okay, I could do that, but I think it's fine. Okay, plus plus mem start. Okay, that's sprite bytes for 1. 702020, cool. And then we need 2, which would just be there. Just do that. Oh, oh God. How did that happen? Okay. Okay, for 2 it would be 0x f0, 10 f0, f0, 10, f0, 101, wait, 80 f0. Okay, cool. Then we move on to 3. F0, 10, F0, 10, F0, 0, F0, 10, F0. Yes, okay. And again, we need plus plus mem start and then 4. Yeah, it's a little tedious, but yeah, it's fine. 0, 9090 F0, 1010. 9090 F0, 1010. Ah, shit. Okay, there we go. Then for 5, F0, 80, 80, F0, 10, F0. Okay, that's 5. Then we have 6. Let's do mem start actually. So if you notice, like 0, 1, 2, 3, 4. So it'll be in multiples of 5, right? For every start of like a new sprite set of sprite bytes, right? So 0, 5, 10, 15, etc., right? So we have how many? 16. So 16 5s are 550. The 80 basically. Okay. And that's we're going to point I to the start location. So either to a 0 or to a 5 or etc., right? I think that's what makes sense in my head at least. Uh, that's what that instruction is going to do. Plus plus mem start 6 f080 f090 80 f090 6 f0 again. Yep, that makes sense. Okay, cool. 7 okay, 7 would be f0 1020 1020 f0 f0. Oh, sorry, f0 1020 4040. Then 8 uh, 8 would be f090 f090 f0. Okay, cool. Okay, now we have 9, 10, 11, 12, A 9 A B, okay, 9 A B C D E F. It's 9. 9 is F0 90 F0 10 10 F0. A is F0 90 F0 9090. Okay, 11 E090. Interesting. E9 E9 E C, which is 12 F088 F88 8 F. Okay, and then D13 is E999E 999E, and then finally no, E after 14 is F8 F8 F 8 8 F8 F8 F. F is F8 F88 F8 F8 8. Cool. Okay. I mean, maybe there might be one, two typos in here, possibly. But let's see. Okay, cool. So this is what will happen when we initialize sprite data. That's cool. All right. Now what happens is we have this new opcode, right? Which is load. I think it was load data. Okay, let's go back. Yeah, load location for sprite for digit vx. Value of I is set to the location. So, okay, to load sprite x loads the location for the hexadecimal sprite corresponding to the value of vx. So, if vx value is 0, that corresponds to 0, right? If vx value is 1, it will be 1 times 5. So it starts at 5. X value 2, 2, 5 times 2, right? So, okay, cool. Loads hexadecimal sprite data location of vx into I. Okay. Why is it doing that? Why is it not letting me? Why is it? Okay, weird. IntelliJ is being weird. Oh, what? Performing editor copy. What is this? What is happening? I can't copy paste. Why is it so slow? What did I do? Did I break something somewhere? Let me commit this. Oh god. Okay. Let's do it the whole way. Oh oh. Chip8. Git status. Git add main dot source main dot c. Yeah, that's it. Commit dash m. Working on instructions. Implementing instructions. Git push. Okay. I mean, we don't have branches set up, so it's fine right now. Okay. We close this. I don't know why it's doing this close and stop. Let's make sure it's working. Okay. Actually, I wanted to check something cool actually. So I was hearing about WebAssembly. C wasm C2 WebAssembly. When you're writing a new code model language, you can compile it to WebAssembly using a tool like emscript. And let's see how it works. Check the emscript and SDK. Creating HTML is C. Okay. First, we need to compile. Take a copy of simple example. Say hello C. Now, using the terminal window used to enter the emscript compile environment, navigate to the same directory as your hello.c file and run the following command. The options we're passing are as follows. Dash o hello.html specifies that we want emscriptor to generate an HTML file page to run our code in, as well as wasm module and the JavaScript glue code to compile and instantiate the wasm, so it can be used in the web environment. Okay, running your examples. Wasm. I think you should see it just compiled C to WebAssembly. Run your browser. Use a custom HTML template. Okay. Hmm. Listen to some person. Okay, I mean that's maybe I should. I'll gonna look into that later, but okay, got a little sidetracked over there. Sorry, guys. Okay, so what happened? Yeah, freaking IntelliJ was being weird. Let me open what I need. Open back up. Home, repos. Oh, never mind. Repos. Chip8 here. Start ID. Connect. After we implement this instruction, I'm gonna hit up the gym actually and maybe eat some food, and then probably come back and work on some more. Deploy failed. What? What the manage ID backends. Let's see. Get rid of this. Get rid of this as well. Okay. New host. Add. Um, equal download IDE and connect.
I swear, they're missing the point.
There we go. Takes a while, huh? Oh my god. There we are. Looks good. Yes. APS/index. Restart IDE. What? What's going on? Check the toolbox maybe. See if there's an update. Alright, I think I'm gonna fix these issues and come back after I get up the gym and eat some food. Thank you so much.